In chapter 10, we're comparing two groups. If chapter 8 and 9, we were just focusing on a single population, trying to estimate that population's parameters, things like population proportion or mean, using either confidence interval or conducting a significance test. Chapter 10's focus is really finding the difference between two population proportion or population averages. Um, I have three lessons in this chapter: 10-1, 10-2, and 10-4. Each of them are going to be about 45 minutes, and that will be really enough for the semester. You will have your last unit exam, your exam 3, which we will just call final exam, on next Friday. So I am officially out of days to teach you. Well, this will be it. This will be it. So after 10-4, that's the last section that we will cover, and that's the last section that you will see on your exam 3. This week's homework, I try to keep it very short, just 10 questions, because I do want to open up on, I don't want to create another required assignment for you. I want to just create like an optional, but absolutely, I suggest you do it. Please work on that practice test, okay? I will create a practice test so that you can kind of practice for your last exam for the semester, and that will be next Friday. Wow, it's going so fast. And what I mean by next Friday, well, I'm recording this on May 5th. I'm sorry, May 1st. Today is May 1st, Friday, and this is officially our last class day, as next Friday will be May 8th, and that is your final exam day. So yeah, we're almost done. So let's get started on the first section, 10.1. We're comparing two proportions. In 10.2, we'll compare two means, and 10.4, we're going to be working with dependent samples. But let's get started on 10.1. Let me open it right here. Open. Okay. Thinking about 30 to 45 minutes on this lesson, and then the other ones too, so that you guys can finish watching and try the 10 homework problems. All right, let's see. First, let's talk about dependent and independent samples. When you make comparisons, most comparisons of a groups of groups use independent samples really. So you may be looking at a sample from a group of smokers versus a sample from a group of non-smokers, or sample from a female population versus a sample from a male population. They're coming from two different groups. These are independent samples. So we will go over those independent sample, how to work with them in 10.1 and 10.2. These are the common ones. But sometimes the samples are going to be dependent. And if they are coming from a dependent samples, then what we have to do, it gets a little bit different. So in 10.4, I'll talk about how to work with them. And when two samples involve the same subject, now how can that happen, right? How can you sample from a same subject? Let me give you an example. And if that happens, we say they are dependent. Something like this. Like if I want to compare my blood pressure, my own blood pressure, like in the morning and in the evening, you see how those measures that I take in the morning and in the evening are both coming from me, right? That same subject being me. So if that happens, then that will be an dependent samples, because like imagine like I'm having a stressful time. Maybe my blood pressure in the morning is high, and then that same blood kind of stress keeps my blood pressure high in the evening. So my blood pressure in the morning may have something to do with my blood pressure in the evening. So um, that's an example of a dependent sample. And how about my left shoes versus my right shoes? So I may spray some shoe protectant on left shoes and my right shoes and see how they do. See how they do. Now, because I can't really leave my left foot at home and just walk out with my right foot. How my left shoe does depends on how my right shoe does, right? So, if samples come from the same subject, then you can say they are dependent. And the things that we have to do in order to um, how should I say? I mean, the studies that the test and confidence interval that we have to do gets a little bit different, a little different when we are working with dependent samples. And one thing that I want to talk about is called matched pair design in 10.4. So we will work with both independent and dependent samples in chapter 10. 1 and 2 are working with independent, and section 4 I will work with dependent then. Okay. All right. I'm just gonna leave 10.3 as like an optional reading for you if you want to read it. That'll be fun. But let's go over those 3 sections in this week. Okay. All right. Before I get started with comparing proportions, let me give you some notations. Okay. The first notation, P. As you know what P is, little p. Little p represents population proportion, right? So guys, I'm working with 2 proportions, 2 populations. So we're going to have little p1 and little p2. P1 represent the population proportion for the first group. P2 represents the population proportion for the second group. Now we got 2 of them. What's our goal in this section? Our goal is to compare them. Okay, our goal is to compare them and see if they have any difference. And look at the word difference. In math class, when we say difference, what do? We subtract, right? Like sum is adding, product is multiplying. Difference is when we do subtracting. So what we're going to do is we're going to subtract P1 minus P2. And if there's no difference, if they're exactly the same, imagine subtracting 2 of the same thing. If you subtract, say, 5 minus 5, what do? You get 0. The proportions, P1 and P2 are just numbers in between 0 and 1. Imagine subtracting 2 same proportions, like 0.70 minus 0.70. If there is no difference, what number are you going to get? 0, right? So this number, 0, will be a very special number in chapter 10, because when we compare and we get their difference to be 0, then maybe they're the same. So we'll talk about this importance of 0 being in our confidence interval more and more. But what we are really doing is we're trying to estimate that population proportion difference. We're doing P minus P1, P1 minus P2, but we don't know what true population proportion is for either of the populations. So what are we going to do? We're just going to try to estimate it by P1 hat minus P2 hat. And when we put hats on top of these P1 and P2, we're just talking about sample proportion, the second best thing, or I guess our best estimate, our point estimate to the P1 and P2, the true population proportion. So same business, right? We're still using our P hats to estimate the P, but this time we're interested in their difference because we're comparing them, right? So last thing, notation, like N. When we just say little n, I was talking about the sample size, right? But now we have 2 proportions, 2 populations, we're gonna have 2 samples. So little n1 and n2 represents the sample size for the 2 groups, okay? So now we kind of talked about these. Hold on. Now we talked about this. I kind of wanted to give you a picture to tell you that we're still working with this sampling distribution idea. The sampling distribution of sample difference is varied around the population difference, P1 minus P2. That's what we are trying to estimate. But we may get a sample difference. P1 hat minus P2 hat, that may be way out there. And if we get something that's way out there, I know you're just coming from chapter 9, where we talked about significance level and p-value. If the probability of observing such extreme sample proportion or sample difference is so low, I mean, what do? Then we have strong evidence against the null hypothesis. Maybe the true population difference is not that. So we're still doing the same idea using this sampling distribution. So we want to talk about the sampling distribution of sample difference, or the population differences, mean and the standard deviation. And our textbook does talk about those formulas, and that is given to you in chapter 10.1. If you want to do this by hand, the formula is listed on your textbook. And all we do is really the same thing. We plug in our variables, our P hat, P1 hat, P2 hat, divided by N1, and it's all there for you. But what I want to focus on this week is really, let's do the technology. Let's make the technology do our test for us so that we can interpret the result. Okay, and that's more fun, I think. All right, so confidence interval first for difference between two population proportions. Now, you know there are two inferential statistics method. We can do confidence interval, try to capture the true population difference, or we can also do the significance test. Okay, confidence interval will be able to capture the true population differences, but here is one number that you really care about. Okay, now when we are comparing groups, guys, when we're comparing two groups, they're either different or they're not that different, right? They're different or not that different. So if they're not that different, if they are the same, then what is their difference going to be? The difference in those two numbers will be what? 0, right? If they're exactly the same, you subtract them, you get 0. So suppose you create a confidence interval for P1 minus P2, and that confidence interval contains 0. Oh, the population proportion may be equal then. It may be, hey, there's no difference. The difference came out to be 0. Maybe they're not that different, or maybe they're equal. So when it does not contain 0, when that confidence interval is completely above 0 or completely below 0, we can infer which population proportion is larger. Okay, so take a look. Suppose you do P1 minus P2. You subtract them, and you get a positive number. When does that happen? Uh-oh. When you subtract two numbers and you get a positive number, when the first number is bigger than the second number, then the subtraction comes out to be positive, right? Say that you do 95% minus 5%. You get 90% positive, right? You get a positive 90%. So if P1 is bigger, then our confidence interval will be positive, above 0, okay? When you do the subtraction, P1 minus P2, and you get a negative number, oh, when you get a negative number, if your confidence interval is completely below 0, then maybe we can infer that P1 is actually smaller than P2. Because if you subtract small minus big, that's when you get a negative number, right? So by looking at whether the confidence interval comes out to be completely positive or completely negative, we may be able to infer which population proportion is larger. But if it includes 0, we're 95% positive or 95% confident that the true population is in that interval, and one of that number is what? 0. That means, well, they may be just equal. Maybe none of them is big. Maybe they are the same. Not one of them is bigger. So that's the idea of confidence interval. What we're going to do is we're going to actually create a confidence interval, construct a confidence interval using StatCrunch, and we will interpret the result in a word problem, okay? So first example for you, guess where I got this from? Your homework. So maybe you'll get different numbers, but then the process will be the same. And I'll promise to keep something like this put something like this on your exam. This chapter is 1/3 of your final exam. I keep saying final exam, exam 3 really. And there's the same thing in our class, but out of those 10 problems that you're going to do for me this week, I may pick like 5 from this chapter, 5 from last chapter. I'm going to try to keep it short because for the final exam period, I'm allowed to give you a maximum of 100 minutes. So it's not going to be like 30 questions. I will keep it as like about 15, definitely less than 20 on your exam 3 or final exam, okay? Anyways, let's get back to this. Confidence interval for a difference of proportion example. Let me see if I'm still recording. Thank goodness I am. Some days I'm like talking, yeah, let's teach. And then like I didn't even hit the record button. And all right, so let's go ahead and do this. Random samples of students at 122 colleges were interviewed several times since 1997. I like that word random over there, guys, right? It's a random sample, so one of the assumptions checked. Sample is random. 122 colleges were interviewed. So how many people, huh? Let's see. But they said, look, they said the word since 1997. So back in 1997, what did they find out? Of the students who recorded drinking alcohol, so they only look at people who drink alcohol, the percentage who reported binging at least 3 times within the past 2 weeks was 42.4%. Okay, that's pretty high. Of how many students? 335 students in 1997. So back when they first collected this data from students back in 1997, they found that 42.4% of 335 students were binge drinking. And I said students, but the alcohol drinking students. And what else? 21.3% of 845 students in 2004. So are we taking the same are we taking two samples from the same group of students? No, right? Students who are in college 1997 are not the same students who are in college in 2004. Right? Unless they're staying there for like so long. But so we can assume that these are independent samples. Okay? Now, that's the number given. So what's the question? What's the question? But guys, as we are reading these questions, we should be thinking about the information. We should be thinking about these information and how we can use our statistics skills to answer some of the questions. This is what I noticed. It was 42.4% back in 1997, and it almost became half, 21.3. It's actually, yeah, it's like half, right? Half of 40 is 20. So I'm thinking, hey, the proportion of people who binge drink is not the same anymore. That's what I'm thinking. But all right, let's see what we want. We want to construct and interpret a 95% confidence interval to estimate the true difference between the proportion of student population in 2004 who reported drinking alcohol that binged at least 3 times within the past 2 weeks to the proportion of students in 1997 who reported drinking alcohol that binged at least 3 times within the past 2 weeks. They make the sentence so wordy, but I see what we are doing. We are just comparing the proportion of binge drinkers in 1997 and 2004. And what we are trying to do is, are they different or are they not that different? And for me, I don't know, when something goes from 42.4% down to 21.3%, I think there is a difference. But we're going to do it by creating a confidence interval. Okay? All right, guys, listen. What if there's no difference? What number are we going to have in our confidence interval? If there's no difference, what's the number that we're going to see in our confidence interval? 0, right? If there's no difference, that means that you subtract them and you get a 0. So if you're going to be 95% confidence, within that range, if that range includes 0, then we don't get to say they changed any. Okay? So kind of just thinking through this, but let's get started. All right, checking assumptions. The response variable is categorical. What does that mean? Okay, what's the response variable? They responded, yes, I binge drank, or no, I did not binge drink. See, the answer was either yes or no. Yes, binge drinking, no, not binge drinking. It was a category. So the response variable is categorical. That's why we are looking at the proportion of people who said yes. Okay, so that assumption is checked. Now, if the response variable is quantitative, suppose something like, how many times did you drink? On the average, how many times did you go out and binge drink last week? And their answer may be like 2, 3, 4, 5, 6, 7, 8, So if they're talking about average, the number, that's going to be quantitative. And we'll look at those in 10.2. But for right now in 10.1, we're working with categorical response variables. Both samples are independent and random. They gave us the word random. They did say the sample was random, and I'll assume that students sampled in 1997 are independent of students sampled in 2004, because they're not the same group of people, right? They're not the same subjects, because the kids who kids who are in college in 1997, they probably graduated, I think. Okay, so last one. Is the sample size large enough? I think so. I think, weren't we looking at about like 800 people? Let me see. Oh, it was 335 students and 845 students. So together, like over 1,000. So I would say, yes, sample size is definitely large enough. So we're good to go on. So take a look. Like I said, of course we can create confidence interval. You do know how to do it. You know how to create a point estimate. You know how to add or subtract the margin of error by finding the z-score, the corresponding z-score for what 95% confidence interval is 1.96, and we went over all that in chapter 8. So right now, how about we use some technology to do the test? Let's do the test and actually work with the interpretation piece in this section, okay? So go here for me, stat, proportion stats, because we're working at proportions, right? And click on this time to sample. Remember, guys, last couple weeks we were working with one sample because we were estimating a single population parameter. And also click on with summary because we were given the summary of this study, not like on actual raw data. So click on that for me. And then what I actually did was I just screenshotted the output, but let me go and do this with you, okay? Because I think it will be helpful for you to see what kind of numbers I'm entering, okay? So let me go open up my StatCrunch right now. Hold on. My math lab. I was having like an anxiety attack because I wanted to cover everything for you guys, but at the same time, I don't want to make it stressful, but this is a different semester, and I think we worked hard and we learned a lot, so that's important. But let me go to StatCrunch and open up stat, proportion stats, and two sample, and click on with summary. Now we were given some summaries, right? Now, the wording's terrible, guys. Think about it. The number of successes, right? Number of successes. And in our example, what were we talking about? Number of people who binge drink, right? So let me go ahead and make, oh, you're seeing my nasty desktop. There's so much stuff going on here. Let me just open up two screens here so that I can see my numbers. So here's my StatCrunch. Okay. So the first sample, let me just make 1997 my first sample. 1997, there were 335 people interviewed. So number of observations is 335. Now, what do they mean by number of successes? And in this case, the wording kind of sucks, but number of successes means the number of people who are binge drinking, okay? So they didn't really give us how many people reported they were binge drinking out of 335. What they gave us instead is that 42.4% of 335 students were binge drinking. So I'm going to go ahead and open up my little calculator. Hold up. Shh. Okay, and then I will find out what is 335 times 0.4, forgot the number, 424. What am I doing? I'm finding out 42.4% of 335 students. What I just found out is that about 142 students answered that they were binge drinking. So enter 142 for number of successes. They successfully binge drink. Okay. Now that's the data for sample 1, right? Now let's enter the data for sample 2. How many observations were taken in 2004? 845. And out of those, they said 21.3% successfully binge drinked. So let me figure out what is 845 times 0.213. Oh, okay. Let's round that up to what? 180 people. 180 people binge drinked. So that's our number of success. All right. So that's the input. Okay. You can watch this. You can look at this carefully. All right. Now, right now, we will do hypothesis testing later in this lesson, but oopsies. For right now, I'm very sorry. For right now, we're doing the confidence interval for 95%. So click on confidence interval for P1 minus P2. We're subtracting, we're estimating the difference in population proportions. And we want the level to be 0.95. We want 95% and hit compute. I think when I first created my Google slide, I used the number instead of the decimals instead of rounded up. But it makes sense for me to say 180 people were binge drinking instead of 179.985 people were binge drinking. So I'm going to go ahead and just change my output table, but we will talk about this output table now, okay? So hold on. Let me go ahead and just change this output table. Shh. My small little doggy is snoring a lot. So I think I have two output tables, but then the most recent one is this one. Let me go ahead and put this one over here. No, it's not gonna let me wake her up and move her somewhere. Go somewhere else. Go. Alright, I'm back. So let's talk about this output table. And you see the confidence interval right there, right? Let me go ahead and present this. So P1 is a proportion of successes for population 1. And what that means is the number of people who are binge drinking, or I'm sorry, not number, the proportion of people who are binge drinking out of all student drinkers in 1997, and proportion of success for population too. In our case, that is the proportion of binge drinking students out of all drinking students in 2004, and the difference in proportion. Okay, difference in proportion. I thought they decreased because the number went down from like 42% to like what, 21%, right? So we're gonna see if it really changed. So you do subtraction. If it really didn't change, the subtraction will give you a 0, right? We should see, if there's no difference, we should see 0 in our confidence interval. These four, count 1, total 1, count 2, and total 2. These are the numbers that we entered. These are our input that we gave them, the summary that we gave StatCrunch. They found sample difference for us, and then they also find standard error for us. And these two, L limit, U limit, that is the lower limit, and the upper limit. This is our confidence interval right there. Now take a look at this. This is a proportion, so both of the numbers must be a number between 0 and 1, right? Hold on one second, because it can be negative. It can be negative because depending on which way we subtract. But it shouldn't be anything greater than 1 or smaller than -1. It can be negative because the way we subtract it. But notice this is the lower limit is about 15% and the upper limit is about 27%. 15 to 27, that is completely positive, right? Does it include 0? It doesn't. This confidence interval is completely above 0. It doesn't include 0. And including 0 means there is no difference. So, is there a difference? Yes, there is a difference because our interval does not include 0. And in fact, the fact that it came out completely greater than 0, completely positive, tells us that the first position, the proportion of successes in population 1 is bigger than what we subtracted. So guess what? We get to safely say that the proportion of people who were binge drinking in 1997 is actually greater than the proportion of students who were binge drinking in 2004. Because our confidence interval came out completely positive, we are 95% confident that the true population difference is captured within this interval. So here is the interpretation of our 95% confidence interval. There is evidence that the true proportion decreased from 1997 to 2004. It went down, right? Because when we subtracted, it came out completely positive. The difference came out positive because I did number from 1997 minus number from 2004. So I did big number minus the small number, and that's how it came out greater. And notice it didn't include 0. Including 0 means that, hey, maybe really there's no difference. But my interval was completely above 0. So we do have evidence that the true population is not only different, but it actually decreased from 1997 to 2004. And that is how you can use a confidence interval to make an inference about the population. Okay, so unfortunately, I know you like math. I know you like math, but this is a formula, guys, that you will need to use if you want to do this by hand. But we kind of let StatCrunch to do that part for us, since we kind of did something like that in chapter 8 and 9. But we focus more on the interpretation of the interval and how not including 0 means that the population proportion is estimated to be actually different. So a quick summary for you. It's talking about how we must have categorical response variable, independent random sample, and a large sample size. Okay. How about this time we conduct a significance test, the second type of inferential statistics. All right. Another different. This is all about binge drinking. It's all about binge drinking in this 10.9 lesson. But let's take a look. In a study of binge drinking, the percent who said they had engaged in unplanned sexual activities, because of drinking alcohol, was 24% in 1993. And the sample size in 1993 was 151 people, and 30% in 2005. And their N was slightly bigger, 483. So they interviewed more people in 2005 compared to 1993, and you notice how n doesn't have to be equal, right? N1 and N2 does not have to be equal in sample size. And what I noticed is this: people who engaged in unplanned sexual activity because they were drinking, looks like it kind of got bigger, like 24% to 30%. Now the thing is though, 24% to 30%, is that statistically significant? So that's the question that we can use to statistics to answer, right? So is this change, oh, they're really typing, yeah. Is this change statistically significant at the what level? 0.05 significance level. And they did a great job because they gave us a significance level in the beginning. Because remember in 9.4, we talked about how you should not wait until you see the p-value to decide on the significance level, right? 0.005 is a safe number to go. So if we get a p-value smaller than 5%, we're going to reject the null. And if we get something greater than 5%, then we're going to just say, hey, we failed to reject the null, that there is no difference. So let's go ahead and do a hypothesis test, okay? Let P be the proportion of students who say they had engaged in unplanned sexual activity because of drinking alcohol. So we define what P is, okay? That's the proportion of people who engaged in this activity because they drank alcohol. Now we can write P1 and P2 then, right? Before I go there, I want to talk about one more thing. Okay, one more thing. Pooled estimate. Okay, pooled estimate. Take a look. The proportion P hat. And you notice how I said P1 hat and P2 hat in chapter 10 when we first started. P1 hat represent the sample proportion from the first sample, and P2 hat represent the sample proportion from the second sample. But what do I mean by just P hat in general? Okay, it's called a pooled estimate because it pools the total number of success and the total number of observation from two samples. So guys, we had two samples, right? Now, how many people did we interview in total? How many people did we interview in total? Let me get my little calculator out. I'm still recording. I got 151 plus 483. So in total, in 1993 and 2005, we interviewed 634 people in total. So out of those total number of people, how many people were engaging in unplanned sexual activity because they were drinking? Now, for that number, I need to figure out what is 24% of. What is 24% of 151? So do 151 times 0.24. So about 36 people were engaging in unplanned sexual activity because they were drinking back in what? 1993. And how many people were doing that in 2005? I can do 483 times what percent? 30%. And that number is, let's just round that up to 445 people were engaged in such activities. Okay, so in order for you to find pooled estimate, you need the total number of people in general, not in general, people who participated in 1993 and 2005, number from both samples, and then you need to figure out the number of students who had engaged in unplanned sexual activity because of alcohol, and that will be your numerator. So just kind of what I did, I figured out there were 36 people out of 100, 500, 151 in the previous year, and the earlier number, and 145 people out of 483 people in the more recent year. So if I add the numerator up, what I get is in total of 181 people were engaged in such activity out of 634 total. So that P hat, called pooled estimate, P hat, comes out to be 0.2285. So if you are ever asked to find the pooled estimate, that's what it is. It's just, it pools the total number of success and the total number of observations from two samples. But, all right, let's go on with our hypothesis testing. Let's write some hypothesis. What's the null hypothesis, guys? Well, okay, first of all, notation. P1, let's make that the proportion in 1993, okay? Proportion of, that long phrase. And P2 is that same proportion in 2005, Of course, that's a different number. So here's hypothesis. Hypothesis, when you write them, the null must have equal sign, right? So the null hypothesis is simple. Now, some books write it as P1 equals P2. We assume that the proportion is equal. The true population proportion is equal. Now, what we're going to do is, in our textbook, we talk about the difference, right? Imagine subtracting P2 from both sides. Okay, what happens if you subtract P2 from both sides? You get P1 minus P2 equals nothing left on the right side, therefore 0. So what we are saying here is, and I'm going to stick to this notation, P1 minus P2 is equal to 0. And that null hypothesis is saying is there's no difference in population proportions. Now, what's the alternative? Now, I think it went down a little bit, but I don't think I should just use one-sided test just because I saw one observation. So to be safe and to be more common, I'm going to go ahead and just do two-sided test. I'm going to assume that P1 does not equal to P2. So if you subtract those two numbers, it may be a positive number or a negative number, but it's just not going to be 0 because they're not the same. That's what we are saying. So this is how you write hypothesis for two-sample test using equal sign, and I use not equal sign because I'm just going to do a two-tailed test. All right, so where do you go? Go to that same place again. Go to Stat, Proportion Stats, and click on two samples because we got two samples from two different years. Click on with summary because we were given summary. And then you run the same thing. Imagine how I got this 151. They gave you numbers, right? I'm sorry, not 151. I got 36.24. You know what? Let me do this together, and then I will update that table. So open up StatCrunch. It is helpful to watch. Go to Proportion Stat, two sample, and with summary. Now let's go ahead and figure out these numbers, okay? Go ahead and make this slide go. Guys, I really want to have, and I don't know how, I want to have like two monitors so that I can go from one to the other. All right, let me go ahead and use this and start typing in my numbers here. Oh, this is from a previous problem. This is what I want now. All right, ready? What did we find out? So the total observation in 1993 was 151. Those are the people who were interviewed in total. And out of 151, how many people engaged in sexual activity because of alcohol? Times 0.24. So about 36 people. So go ahead and say 36 people got into that activity. All right, in 2000 what? 5, there were 483, and it's funny because they say successes. How many people successfully engaged in unplanned sexual activity because of drinking? We will do 483 times 0.3, and that number is 145. Okay, so that's it. And notice the last example we did confidence interval, but this time let's do a hypothesis test. We do subtracting, and then hey, if there's no difference, the difference will be 0. And I'm doing two-sided test, so here's the not equal sign. I'm going to go ahead and compute. And let me go ahead and bring this table to my slide so that we can interpret the result. So we kind of did we skipped a lot of steps because we were doing the test and the confidence interval on StatCrunch. But again, I want to focus on interpretation in chapter 10. So here we go. Let's talk about this now. Two sample proportion summary, hypothesis test. 1, 2, 3, 4. Notice these 4 are the numbers we gave them, right? It reported back the sample difference, standard error, and z-stat and p-value. Now z-stat is the z-test statistics, right? That's how we called it. And it is negative. It's negative. And it's about 1.46 standard deviation below the mean, right? with a p-value of what? 0.1422. Now, what was your alpha level? What was our alpha level? Significant level was 0.05. So compare that p-value, 14% to 5%. Is it smaller than 5%? No. Oh no. So, do we have a strong evidence against the null hypothesis? No. P is too big. P-value came out way too big. 14% chance this could have just happened by chance. So, make a decision using a significance level of 0.05. You notice it came out to be 0.14. It was 14%, and compared to 5%, 14% was too big. We do not have sufficient evidence to reject the null hypothesis, so we are unable to show that there is a difference in proportions of reports of engaging in unplanned sexual activity because of drinking between 1993 and 2005. So we're saying it's probably about the same. Now, suppose, and the next thing that I'm gonna just do right now is not on the Google slide, but remember, two-sided test and a 95% confidence interval, they better have the same result, right? So what if I go back to that same place, stat, proportion, where are you? Proportion stats, two samples and summary. Hopefully, oh no, they deleted everything. Let me just go ahead and write down 36, 151, 145, and 483. And then ask them to do a 95% confidence interval. Okay, compute it. Guess what number we're going to have in our interval? Guess what number we're going to have in our interval? Take a look at this interval for me. Negative 0.152. Oh gosh, it's a tricky case. You notice this number is almost 0, right? So I wanted it to be negative on one side and positive on the other so that I can say, hey guys, this interval includes 0. But this is just very, very close to 0. So this wasn't too good of an example that I just wanted to kind of do. But the confidence interval at 95% confidence level and the result from a significance test at alpha level 0.05 should give you a consistent result. And I think it is the consistent result. It's just the upper limit is so close to 0, really. So, well, that kind of happened. But using significance test alone, we just say that we don't have sufficient evidence because our p-value came out a little too big. Now, that was really all I wanted to do, but then here's a summary, by the way. Notice how we skipped a lot of steps like test statistics. Not a lot, really. We just didn't find that using it, but there is a formula for you if you want to use the formula. Notice how p-hat, the pooled estimate, is getting actually used here, but we really focused on the conclusion part. I want to do one more. A study used 1320 patients who had suffered a stroke. Okay, big sample, by the way. The study randomly assigned each subject to an aspirin treatment or a placebo treatment. Also, some people are actually getting some aspirin, some are just getting placebo, fake pills. The table shows a technology output where X is a number of deaths due to heart attack during a follow-up period of about 3 years. Sample 1 received a placebo and sample 2 received aspirin. Hopefully they did blinding, right? Remember the blind test? So they don't know well, that's what they are doing, right? They're giving one group a placebo, so they may think, oh, I'm getting some kind of drug, I feel better. So to prevent the placebo effect, they're giving one group a sugar pill. It looks exactly the same. All right, so we got an output there, and I don't know what they used, but I think we got everything that we need to interpret the result. They gave us the 95% confidence interval. Look at that interval for me real quick. The left end is what? Left endpoints, or I should say the lower limit is negative 0.0092. It's a negative number. And the upper limit is what? 0.0, a positive 0.029. So guess what this interval includes in the middle? What number is in the middle? It includes 0 in the middle, right? And including 0 in the middle means that, there may be no difference. Because 0 means there's no difference, and we are 95% confident that the true population difference is population proportion difference is within these two numbers. And because 0 is one of the number, maybe there's no difference. Now, what about the test for difference? Look at the p-value. P-value came out to be pretty big, like 31%, and an alpha level of 0.5, it will definitely fail to reject the null hypothesis. So this is great because they agree on the result. I wanted to see that on the previous example. Sorry that really didn't work out as I wanted. But let's state the hypothesis that we're getting tested. Let P1 represent the population proportion of stroke victims receiving aspirin who died due to the heart attack, and P2 represent the population proportion of stroke victims receiving a placebo who died during the heart attack. So what we're going to do in our null hypothesis is that assume they are the same. That proportion is the same. So if they're the same, you subtract, you get what? 0. So the null hypothesis is going to assume that their difference is 0. There's no difference. Now, the other one, we're just going to assume that they are not equal to 0. We're doing a two-sided test, right? Two-sided. And remember, two-sided test tends to get higher p-values, like exactly the double p-value. And could that be the reason? Could that be the reason that we may have failed? Well, we'll take a look. We'll take a look at that soon. Let's interpret the p-value for the test. Remember, the p-value was 0.3103. If the null hypothesis were true, the difference at least this extreme between these two proportions will be achieved at 0.3103 of the time. So what they are saying is the probability of looking at such different proportion in these samples are about 31.03%, well, about that much to happen just by chance. And that's way too high. That's not strong enough for us to say that is highly unlikely. So that's why we're gonna say we failed to reject this test for difference. What if this was a one-sided test? What will happen to the p-value if this was a one-sided test instead of two-sided test? The p-value will be half of that 31.03%. So the p-value will be 0.155, but you see how that's still bigger than 0.05, so still fail. It's gonna still fail the test for significant the difference here. Okay. And I keep mentioning this word significance difference. What does that mean? The two groups are called statistically significantly different if a test based on comparing, oh my goodness, not pairing, comparing two population parameters result in a significant result. And what do we mean by significant result? That p-value comes out to be smaller than the significance alpha level of commonly 0.05. So if you do the test, you got the p-value smaller than 0.05, then we get to say, oh, they're statistically significantly different. Okay? All right. Kind of, I think this may be it. Just want to talk about sample size a little more. Sample size. Now, what happened as you, kind of play with the sample size. Let's talk about working with a smaller sample size first. Now, sample size is what's getting divided, right? Now, imagine making the sample size smaller. You're dividing by a smaller number. If you divide, all right, in a real number, just kind of divide it for you. If you divide 50 divided by like 45, that's a big number. 50 divided by 45, you get 1.111, right? But what if you divide that 50 by a small number of 2? 25, right? So if you divide by a small number, you get a bigger quotient. Agree? Right? If you try to split a cookie with a small group of people, you each get a good amount of cookie. But if you split a cookie with a big group of people, then each of you get like nothing. So as the sample size gets larger, as the sample size gets smaller, look at the location of the sample size, the standard error gets bigger by the way the standard error formula is set up. And that's not what we want. Who wants to have a big error, right? So let's continue. What happens if the standard error gets bigger? Now, remember, standard error is actually the the denominator of our z-score, our test statistics. So as larger standard, as we get standard error bigger, that's going to make our test statistics get smaller. And remember, test statistic is how far away is this number from the true population, the hypothesized null proportion. So because a smaller test statistic has a larger p-value, a smaller sample size means larger p-value when compared to bigger sample size. Now, I think this can be a little bit confusing, but because you may get a case like this. You get a big sample and you notice, you work with the smaller sample and then you got a smaller sample difference, say, but then that smaller sample difference may not have any smaller p-value compared to the one that you will get from a bigger sample size. So just a little tricky parts about how the sample size plays in p-value, and they're all related as one being a denominator in another's equation, just based on the formula. But I think I saw a problem like this on your homework, so just kind of wanted to touch on it, but I don't think that was all right. But all right, so how big should a sample size be? The small sample inference for comparing proportions. The confidence interval for a difference of proportions specifies that each sample should have at least 10 outcomes of each type. 10 outcomes of each type. For one sample, we were just looking at like 15 for the number of success, 15 for the number of failures, but we want to have at least 10 outcomes for each type in each sample. The smaller sample size, I guess we can still go on with this, but the method may not work too well, as the sampling distribution may not be normal. So in the next chapter, if you're taking Stat 2, you'll talk more about what to do if you are really working with a small sample size. But for our class, our statistics ones, we're just going to work with large enough samples so that we don't have to worry about that part, okay? Now, I was trying to keep this as like 30-minute lesson, but now I ended up recording for 52 minutes, and I don't think I was actually going any slow either. So maybe it is perfect that we go over just chapter 10 instead of 10 and something else. I'll be back with 10.2 very shortly. Let me go ahead and first process this video, okay? I'll see you later.